All right. So now in this one, we're asked to find the Taylor series for sine of x. So this is going to be very similar to what we just did for cosine of x. All right. First of all, I need f of 0, and that's easy. That's 0, right? So, and if I take the derivatives of sine of x, I get another pattern. The first derivative is cosine of x, right? The second derivative is going to be the derivative of cosine, so you get a negative sine of x. For the third derivative, you get a negative cosine of x, right? And then for the fourth derivative, you get the positive sine of x again, okay? And then it's just going to keep cycling. So the derivative at 0, all these derivatives at 0, let's evaluate those. And so f prime of 0 is 1. The second derivative at 0 is going to be 0. The third derivative at 0 is going to be negative 1. And then the fourth derivative at 0 is going to be 0 again. And then they'll just keep cycling, right? So the first derivative is the same as the fifth derivative. Maybe I'll write that in here, f5. And this is also equal to, the second derivative is the same as the sixth derivative. And the third derivative is the same as the seventh derivative. And the fourth derivative is equal to the eighth derivative. All right, so we have this pattern. So let's write the Taylor polynomial just using the formula. All right, so the Taylor polynomial for sine of x. Now, in this case, the first term, the f of 0 is 0. So we're going to start with the first order term. And the derivative of f prime at 0 is 1. So 1 times x is just x. The second order term goes away because the second derivative is 0. So let's go on to the third order term, the third degree term. And the derivative is negative 1, right? So I'm going to put a minus 1 over 3 factorial. And then I want it to be times x cubed. All right. All right, so if we go to the fourth order term, it's 0. So if we go to the fifth order term, we're back to 1, to positive 1. So it's going to be positive 1 over 5 factorial, x to the fifth factorial. And then the seventh order, there's a the seventh degree term is going to be a negative 1. So I'm back to minus 1 over 7 factorial, x to the seventh, and so on. That gives you enough to see the pattern. All right, so general term. You have to kind of think about it. For cosine, we saw an even pattern. Now we're seeing an odd pattern, right? So, you can write this as 1 over 1 factorial. So you can see 1, 3, 5, 7. And so we need odd numbers in the denominator, odd factorials in the denominator. So I'm going to let k equal 0, 1, 2, and so on. All right. And in order to get those odd terms in the denominator, just remember that an odd number is always one more than an even number. So if I take 2k and I add 1 to it, I will get an odd number no matter what. So I want to start with 1, though. And if k equals 0, okay, that works, right? 0 times 2 is 0, and I have plus 1. So if I start with k equals 0, this one will give me a 1 factorial in the denominator. When k equals 1, I end up with a 3 factorial in the denominator. So that'll work. I also have these alternating signs, right? So I want a negative 1 to the k power. Now I have to always make sure, though, that I've got the right thing, because I want negative 1. I want this to be positive for k equals 0, right? And that seems to work. So when k equals 0, this is positive. When k equals 1, it's negative, and k equals 2, I get positive again, right? Because anything squared is, or negative squared is positive. All right, and then I have x to some power, and I only have the odd powers. So I can again just use 2k plus 1, and that will give me the odd powers that I want. All right, so there's an expression for the general term of this Taylor series. All right, I'll meet you in the next video.